In this segment, we're going to develop an expression for entropy change. And before we go too far, I want to talk about why we came up with this idea of entropy in the first place. Well, early heat engines, power cycles, steam cycles were highly inefficient. For a given amount of heat that you put into the cycle by combustion, you only got a small amount of usable work out of it. And people began to notice that there seemed to be a relationship between heat dissipation, heat lost, and frictional effects, and the loss in energy availability, the loss in the ability of energy to do usable work. And it was Clausius that sought to quantify, well, for a given amount of heat that I put into the cycle, what's the maximum amount of work that I can get out of it? And he came up with a mathematical relationship called the Clausius Inequality, and that became the jumping off point for defining a property that would allow us to quantify that loss in energy availability, and that property ended up being entropy. So let's look at that inequality. Doesn't look like an inequality yet, but it will shortly. And let's look at each individual part of that equation. So the first thing you see is a cyclic integral, which means that it's the integral taken over the entire cycle. So a cycle is made up of multiple processes. Say you've got 4, you just take the integral over each and every one of those processes. That Q, and it's considered in differential amounts, it's the differential amount of heat transfer across the boundary at a certain location within the system. That temperature is the absolute temperature at the boundary, so the B subscript in the equation that represents boundary. And what we mean there, if you want to visualize it, so say you've got a piston cylinder here, and if the surroundings are hotter than the system itself, you can imagine that maybe within your system, maybe it's colder in the middle, but it's hotter on the outskirts. So as you get closer to the surroundings, the temperature increases. So the temperature at the boundary, it's the temperature right at that dotted line. And in this class, you'll be given the temperature right at that dotted line if you're asked to do anything with this, because calculating that is more of a heat transfer concept, and it's outside the scope of this class. But there is one special case that you would be able to figure out what the temperature at the boundary was, and that is for a constant pressure phase change in which the temperature is constant throughout your system. So if you're in that two-phase region and you're going through a process that the pressure is constant, temperature is going to be constant too. It's just going to be the saturation temperature. So that's the one exception to the rule of you'll be given this information. If it were that case, then you'd have to figure that out yourself. All right, so this sigma, this is the amount of entropy produced during the cycle, and it's that quantity right there that Clausius was after. That's the energy that is no longer available to do usable work. If it's equal to 0, that means you have no irreversibilities in your cycle. If it's greater than 0, it means that you have irreversibilities within your cycle. You get an irreversible cycle. So I can replace that and put an inequality in there. So this quantity right here, it's less than 0 if you've got irreversibilities. It's equal to 0 if you have a reversible cycle. All right, so what we're going to do now is we're going to take that equation, which seems to be only applicable for cycles, and try to extend it to a process. All right, so what we're going to do is we're going to look at 2 cycles, and these cycles are made of internally reversible processes between states 1 and state 2. And when we say internally, we just mean that there are no irreversibilities within the system itself. We're not really worrying about the surroundings. All right. So the only restriction on this is that they're reversible. There's no irreversibilities within our system. So if I wanted to define that cyclic integral for the first cycle AC, well, I'm looking from 1 to 2 along path A, and then path 2 or state 2 to 1 along path C. So my cyclic integral, well, since it's an internally reversible process, that's equal to 0, but I could also kind of divide up and calculate that cyclic integral. So I've got the integral of this differential amount of heat transfer divided by T, but divided by the temperature from 1 to 2 along path A, same thing along path C from 2 to 1. Now I'm going to do it for cycle BC. So I'm looking from 1 to 2 along path B, from 2 to 1 along path C. So same thing, this cyclic integral is equal to 0 since it's all reversible. And then I could kind of divide it up along each one of those processes. And now I'm going to combine them together. I'm going to subtract one from the other. And I notice since, well, each one of those are equal to 0, 0 minus 0 is 0. And then the other thing I notice, when I subtract one from the other, there's I've got the same term at each one of those, and so those are just going to subtract out, and what I'm left with is that the integral from 1 to 2 along path A is the same as the integral from 1 to 2 along path B, which means it does not matter what path I take. It's independent of the path. And Clausius realized he had a new property, which is awesome, because a property is independent of the path. It doesn't matter how you got there. It's just a function of the state itself. So he took this differential amount of Q over T for a reversible process and said that this was equal to ds, S being entropy. And then if he took the integral of that, took the integral of ds, that's delta S. There's our change in entropy. And the units on that are going to be kilojoules per Kelvin or BTU per degree Rankine. You could also put that as m delta little s. And delta little s is an intensive property, and it's on a per mass basis. And that's something that you can actually look up if you've got thermodynamic tables. So if it's compressed or superheated, you just read it right off the tables. If it's compressed, you can make an approximation that it's equal to S sub F at T, not P, you'll get a big error, at T. If it's saturated, you can look in your saturated tables, and you've got a value for S sub F and S sub G, and as you might imagine, you just calculate it based on the quality in the S sub F and the S sub G. All right, so kind of pulling things together, we see that this integral right here is equal to m delta S, and it's equal to 0 if the process is reversible. Vocabulary term. If delta S is equal to 0, we call that process isentropic. So isentropic, important word. That means no entropy change. And the other important concept to grasp is that if a process is adiabatic, meaning that Q term is equal to 0, and it's reversible, so both of those things, it's reversible too, then it's also isentropic. So that's an important thing to realize. If a process is adiabatic and reversible, it's isentropic. And you can flip it the other way. If it's isentropic, that means it's adiabatic and reversible. Adiabatic and reversible. So just because a process is adiabatic doesn't necessarily mean it's isentropic. It has to be reversible as well. So it's a lot of abstract concepts. So you might be kind of confused about like, where are we going next? What are we going to do with all this stuff? So first we're going to develop a few equations for calculating changes in entropy. And then we're going to sort of pull it all together and see how that stuff that we came up with, how those equations that we came up with, how does that actually relate to the loss of available energy for a process. And we're going to do it for a closed system and an open system. So I think once we start working some problems, some of this will clear up a little bit. Yeah, let me know when you have questions. I'm sure you will.